All right, hello and welcome. Today we're taking a look at the gRPC source code. I spent some time earlier this morning putting together a schedule for future videos. I'm going to continue to live stream them all, um, mainly because I like the live stream format. I like recording, my first look at a code base, and I don't want to start editing things too much and cleaning things up too much, because I think that kind of takes away the feel of um, getting to see someone explore a code base that they're not very familiar with for the first time. So here's let me see. Can I let's see? Can I do this? No. Let me bring this out for a second. Okay, so here's the schedule that I have, and you can see this on my YouTube channel. What I've done is I've divided things into what I'm calling theme days, and these aren't all, the days aren't always going to be the same. So right now I've got Meme Gen Monday, which is named after the internal meme site at Google. I just needed an M word, and that was one that came to mind. Um, and so Meme Gen Monday is going to be about going through the source code of Google developed programs, Google source code, but also to some extent, if there's something internal that's known to the outside world, and there's not a Google open source version of it, often there will be kind of either a clone of it or an open source piece of software in the same, essentially the same direction. And I may look at some of those as well. That's mainly for ex-Googlers like myself, who may not be as familiar with the external world. A lot of times, if you spend a lot of your career in Google, then you get very familiar with the Google tooling, and then the outside world, it kind of seems perplexing. So I may do some of those as well. Tools Tuesday, I'm going to devote to a lot of the Unixy, Linuxy developer tools that may not be as exciting, or which some people might take for granted. For tomorrow, I'm going to do Emacs. That I don't think that is a tool that anyone takes for granted. But next Tuesday down here, I'm going to do SED, and I'm planning to do a few of the at least a few of the old school Unix tools like sed, awk, grep, those sorts of things that people use every day and maybe haven't really thought about implementation details of. And then we have Network Wednesday is going to be devoted to networking stuff. I'm going to start out with the Linux network stack. That's going to be a whole lot of stuff. I'll probably focus on mainly the IPv4 TCP implementation, but I may look at other stuff kind of depending on how I'm feeling. Then Theme Thursday is going to be a reserved day of the week where I'm going to explore different themes. In the past, I've explored themes kind of informally. I think the first few videos were about web browsers, and then there were some videos about there was a video about the kernel, and then there was some stuff about compilers. And then last week I was looking almost exclusively at video game engines, video game emulators. So that theme stuff is going to be kind of slotted in on Thursday for now. I may occasionally do theme weeks, or I may decide that this setup doesn't make sense at all, and mainly do theme weeks. We'll see how it goes. And then Friday is a little bit of a wild card. It's going to be a mix of what I'm calling Fun Friday, which is more for open source projects that are for fun or for creative folks. And so this Friday I'll be taking a look at I think you pronounce it Kdenlive, the KDE video editor. So that's this week, and then next week on Meme Gen Monday, I'll be looking at the Basil's rules, Python rules. I'll be looking at SED on Tuesday. I'll be looking at TCP dump for Network Wednesday, and then for Theme Thursday, I'll look at Cabal, and then finally on Friday, I got a comment asking me to look a little bit deeper at some of the web browser stuff. There were a few requests in there. The one I think I want to tackle first is the Brave browser, which is built, I believe, on the Chromium source code that I had already looked at. So that will give us a chance to look at how people might extend the existing Chromium code base to do additional things. I think I didn't say what the current theme was for Theme Thursday, but the current theme maybe for the next 4 or 6 weeks is going to be Haskell build systems. So I'm going to start with a Hadrian build system for GHC, which we ran into when I was looking at the GHC code. And then on Thursday, I'll be looking at Cabal, which, if I understand correctly, Cabal is I don't want to say default. It's like the low level package manager that things like Stack build on top of, I believe. Okay, so that's the schedule, and that's that. All right, so let's take a look at gRPC. If you're not familiar with gRPC, it's an RPC framework. RPC is remote procedure calls. A lot of developers are familiar with things like REST, where the basic premise of a remote procedure call is that it's trying to be like a procedure call local to a system, except you're going to call essentially a function on another machine. And the idea is to get the API of calling a function on another machine to look as close to what it feels like to call a function that doesn't go over the network. That doesn't go over the network. And so RPC frameworks have a long history, going back certainly in the 80s. gRPC is one that Google developed and open sourced, and is based on their internal stubby RPC framework. Now, my experience at Google, which is current as to maybe about a year ago, is that stubby was still used internally almost exclusively, and then you added gRPC support when you needed to. So I wouldn't quite call it a second-class citizen, but I think when I was there, certainly Google was in the process of making gRPC as good as as good as stubby. I think when I joined, there was some training course, and somebody remarked that gRPC is that stubby is what gRPC wishes it were, I guess. So that's one way of looking at it. In my experience with certainly with my experience with stubby, was it's really nice. It's way nicer than something like REST. And that may not be obvious to you unless you've used both of them pretty extensively. REST and directly making HTTP calls are you can get a bunch of the same features, but the developer experience is not as good as with an RPC framework. So what is the framework doing? It's doing a few things. One is it handles all of the HTTP requests under the hood. In the case of gRPC, it's using HTTP2. So it can do things like bidirectional streams that you might associate more with WebSockets, but now it's being kind of built into the HTTP protocol. But another really important thing that gRPC does is it has an interface description language in IDL, and in that language, which for gRPC they use protocol buffers as the IDL. So you write your API in this interface description language, and then all the code for making requests to the back end or for handling requests on the server end are created from that API description using code generation. And that's really nice because your API has like types built in. A lot of times when you're doing making REST requests using JSON, everything is really fundamentally a string. And if everything is fundamentally a string, that's very flexible, but it's also a little bit maybe flimsy. Like you can't build a house out of super flexible material. And similarly, like a theme of engineering is that like you want to have some sort of rigid structure. And in for programming languages, that's typically like a nice type system. And so that's one of the things that I really like about gRPC. I guess we can look at a code example in Go. So here's an example of a proto file. This is a protocol buffer file. It says that we're declaring a service that's called the greeter service. It's got a single RPC or remote procedure call. And you can call say hello, and you're going to pass it in you're going to pass it in a hello request, and it's going to return a hello reply. And that's your API. And then here's what a hello request is. It has a string, which is name. And this is a field, name is a field of the message. And it gets I don't actually know what this number is called, but it gets a number. And that number is used to pack the protocol buffer message so that so you can pack it efficiently and send it over the wire. And then you get a hello reply string message equals 1. And then here's an example of an extension of the same of the same API. So we've added say hello again, and it's going to take a hello request and a hello reply. And then you're going to call this protoc, which is the proto compiler, and that's going to if you call out with the Go gRPC plugin, it's going to generate Golang code for you. And then you import that code. And I bet we can find an example. Yeah. Okay, so here's a snippet from greeter client main.go. And this say hello again. The say hello again function is going to use the protobuf generated files, the types from those files, including things like hello request and hello reply. And then there's going to be some boilerplate for just setting up the server to call to handle requests. I want to see if I can maybe find this full example. Yeah. I wonder if this has got the somewhere there's an example here. So we can look at a server. Here's main.go. And there's not much to it, right? So PB is the generated file. We're going to tell it what port to use. And we've got this server struct, which is going to implement say hello. And then we're going to, for the main function, we're going to parse the flags, tell it what port to listen to, create a new gRPC server using the gRPC library here. And then we're going to register the server. We're going to say that here's the thing that's called server that we defined up here is the implementation of the API in the PB file. And then we're just going to call sserve. And that's really all there is to it. So here's the implementation of the handler. We're just going to accept the request and populate a message. Okay, so that's kind of what it looks like to work with gRPC. I guess I should mention there's a couple of downsides. One is that you want to make sure that the server and the client have the same implementation, and so are generated from the same proto file. And for that reason, typically gRPC is used on the back end, like within a data center. Everything will speak gRPC, or in Google's case, Stubby. All the microservices will speak Stubby or gRPC to each other. And then to get a request from the outside world into the data center, typically you would use REST because that's what things like browsers support. And so in that sense, at least within Google, REST is kind of you accept it from the outside world. You don't really use it internally, and that's kind of the pattern. And so there are things like proxies that you would put to intercept requests, and they would translate a REST request into gRPC, and then that little thin proxy is the only thing that really needs to understand REST in the stack. So that's what gRPC is about. I'm looking at their GitHub page here. And one thing I noticed is this. I just happened to see this. It says fix erase on vptr, which I guess is vpointer, for unimplemented async request. I think that's too interesting to ignore. So let's maybe start here. I don't know what the X means in GitHub. Does it mean? Okay, so it says it's reported in this bug. Let's take a quick look at the bug. Unimplemented async request constructor races with generic async request causing crashes. This bug is very old. Exact version doesn't matter. Recently, we started to see our gRPC servers crashing right after the call to CQ next. Debugging showed that next returns true, indicating the event is available. However, tag turned out to be null pointer. Since we cast it to our interface and call a method on it, this caused crashes when loading a vpointer. I don't know what language this is. Does it say? We use Clang, but the compiler doesn't matter. Call CQ next for multiple threads. All right. So something was detected by TSAN. The thread sanitizer, I guess, automatically detected a data race. Thread sanitizer reports a data race between CQ worker threads. Hard to reproduce, needs several hours of request flow. gRPC version we're using is this. Okay. So there's some stuff about reproduce. Okay, so let's see what they the cause is that the server requests a call for unimplemented async request in its base class generic async request when the vpointer still points to the base class's vtable. If the call went in and another server thread picks up the tag before the vpointer points back to the derived class's vtable, it would call the wrong virtual function, and also this is a data race. The fix makes the request of the call inside the derived class's constructor. Okay, so what does the fix look like? Well, in the server interface, this is CPP. We're going to add a new parameter, issue request equals true. And then it's a protected variable. And we're in server CC, we're going to add, let's see, this line looks the same, except we're adding the issue request. And if issue request, we're going to call this issue request function. We're going to add a server interface. Oh, we're going to add the function issue request to the interface. The following call start batch is internally generated, so no need for an explanatory log of failure. And we're going to do some sort of assert, I guess, in case of failure of the gRPC request call. Request call. So issue request is going to make this call, I guess. And issue request here instead of base class to prevent race on breakpoint. And so we're moving issue request here. Okay. And then there's what is this? There's some testing to make sure it doesn't happen. Okay. So there's some race, and they fixed it. Okay, so let's look at source. I think, yeah, we already looked at examples. Summer of code, I don't think we need to look at. I'm not sure what templates is. Tests. I guess we might as well look at tests. Just to see what's here. Build test, core CPP, distrib, HTTP2 test. What is CPP? So code generation client, I guess, yeah, thread manager, test server security. So the gRPC code itself is implemented in C++, and then it also supports C++ servers and clients for gRPC. And I think that maybe those are tests for that sort of thing. Here's tests of the core gRPC features. We see things like channels, bad SSL, back off, which I'm going to guess is maybe back off algorithms. AVL, that's a kind of tree, right? I think that's a self-balancing tree. Compression, config, debug, filters, GPR, handshake. Yeah, promise. Okay, so lots of tests. Maybe let's look quickly at the backoff test. So we're going to import gtest and gRPC, and we're going to test constant backoff. I don't know what min connect is. No jitter backoff, I guess, which is a kind of okay, so that's going to test something about the jitter. We're going to set jitter to jitter, and jitter is 0. Okay. So I guess when it's backing off, you can pass in a jitter to prevent it from having like periodic behavior in the back. Like one of the things you have to worry about is if you have like 1,000 requests, let's say, and they're all backing off at the same time, you want to give control over the way that they back off, so they're not all like periodically. They're all going to be exponentially backing off, but you don't want them to all back off and make their requests again at exactly the same time, because then you haven't solved your problem. So I think maybe that's what jitter is about. I'm not positive. Here's some more jitter testing. Okay, cool. AVL, we've got, AVL fuzzer corpus. Is AVL a fuzzer? libavl.h. See if you can find this file. So they're going to fuzz whatever this AVL thing is. What is AVL? So class AVL is going to have an add, remove, lookup below. Yeah, I think this is an AVL tree. Yeah, this looks like tree stuff. Okay, got Q sort. Okay, so that's a quick look at tests. Let's look at source. So in source, we've got abseil CPP. I don't know if that's maybe just a reference to the abseil library, so that the gRPC people have it. It's just got some YAML in it and a Python thing to build YAML, I guess. Let's look at mainly core. C areas, I think, has something to do with DNS. Boring SSL is like a fork, I think, of SSL that that removes features to reduce the attack surface that's used at Google. CPP, I think, is going to look like the CPP test directory. And here we see other languages, which is going to lend credence to my theory about what the CPP directory is up to. So we have C#, Objective-C, PHP, which I did not realize was a first-class citizen for gRPC, Proto. I guess let's see what's in the Proto directory. Python, RE2, which should be regular expressions, Ruby, UBP, and zlib. I don't know what UBP is. I forget what zlib is. That compression? Yeah, actually, let's look at C areas and this other stuff. And core is where the real action is going to be. I'm almost certain. So let's take a quick look at C areas. And this just has a file to upgrade the dependency C areas. Okay, so we'll ignore that. Zlib is the same way. Actually, let's take a quick look at this is some sort of hacky build tool stuff. Out of curiosity, I'm going to look up what zlib is. Yeah, compression. Okay. Software library used for data compression. Is the compression algorithm called zlib algorithm? Zlib only supports one algorithm called deflate, which uses a combination of a variation of LZ77 and Huffman coding. All right. And then UPB, I'm not sure what that is. Maybe I can look that up. Software drivers. Universal power line bus? Home automation. I'm not sure that that's it. What if I just look up UPB? UPP message internal. Third party UPP. Small fast C protos is a small, micro protobuf is a small protobuf implementation written in C. It's the core runtime for protobuf languages extensions in Ruby, PHP, and soon Python. It has comparable speed to protobuf C++, but is an order of magnitude smaller in code size. Okay. So it's a small protobuf implementation that tries to be fast. Okay, here we are in gRPC /source/proto. We've got gRPC and math in this gen build YAML file. Okay, so these are, I guess, protocol buffer definitions of different APIs for the gRPC server. So I recognize these. Channel Z is going to be like channel metadata that you can serve from your gRPC server pretty easily. Health is going to be health data, like is the server still alive, or is it unhealthy and you need to choose another backend. Reflection is going to be, I guess, looking inside of the server will be aware at runtime of what its API is. Lookup, I'm not sure. LB should be load balancer. And status. I'm not sure how status is different from something like health. So here's lookup, RLS proto. We've got a root lookup request. Allows the client to specify what kind of target format it would like from RLS to allow it to find the regional server, e.g. gRPC. Possible reasons for making a request. We got unknown, miss, stale. Route lookup request. Okay. Maybe this is supposed to be like kind of like DNS. Prioritize list, best one first of addressable entities to use for routing. Using syntax requested by the request target type, the targets will be tried in order until a healthy one is found. Okay, so this is, I guess, helping you look up backends. I think. Load balancer. I thought load balancer they stopped support of, but I'm not sure. So there's some load balancing request stuff. You can get client statistics and fallback response, initial load balancer response. Server list is going to return a list of servers selected by the load balancer. The server has an IP address, a port, a load balance token, an opaque but printable token for load reporting. The client must include the token of the picked server into the initial metadata when it starts a call to that server. The token is used by the server to verify the request and to allow the server to report load of the gRPC LB system. Okay, so they're going to give you a token, which is, I guess, kind of like a bearer token. And they're going to use that, I suppose, a little bit similarly to a distributed tracing thing. You pass the token in with the request, and that helps them keep track of what requests are going where and what has a lot of load. And indicates whether this particular request should be dropped by the client. If the request is dropped, there will be a corresponding entry in client stats calls finish this drop. I don't know why you would request that your own request is dropped, but I'm sure there's a reason. Status proto. All right, status defines a logical error model that is suitable for different programming environments, including REST APIs and RPC APIs. It is used by gRPC. The error model is designed to be simple and flexible. Okay, so status. This is just a gRPC status code. So the status code, which is like an error code and a message, and then any details. Okay, so like this. Where's there a enum? Shouldn't there be an enum? The status proto is copied from here. Yeah, somewhere, let's see. Code.proto. Yeah, okay. So status code can be okay, canceled, unknown, invalid argument, deadline, exceeded, not found, already exists, permission denied, unauthenticated, resource exhausted, failed precondition, aborted, out of range, unimplemented, internal error, like an internal error, unavailable, or data loss. So this is kind of an alternative to the HTTP error codes, like the 401, 403, 500, etc. Right, health.proto is going to tell you how healthy it is, whether it's unknown, serving, not serving, or service unknown, only used by the watch method. Yeah, I don't know what service unknown is about. And so you can check whether a server is serving. And channel Z is going to have channel metadata. It's going to have an identifier for the channel, data specific to the channel. Channel ref. We've got multiple channel refs. There are no ordering guarantees on the order of channel ref. There may not be cycles in the ref graph. A channel ref may be present in more than one channel or a subchannel. And a subchannel ref and a socket ref. There are no ordering guarantees on the order of sockets. Subchannel is a logical grouping of channels, subchannels, and sockets. A subchannel is load balanced over by its ancestor. Okay, so the gRPC has a notion of a channel. I'm not really sure how it works in outside of Google. But outside of Google, everything uses DNS. Internally, there's some addressing system. There's some comedy sketch. I'll link it in the show notes. There's some comedy sketch about microservice development, and I think one of the microservices they talk about is essentially this DNS-like service where you have to make a request to it, and it will tell you what the server backends are, right? And so that's kind of what DNS does. You ask it where example.com is, and the DNS system returns a list of IP addresses. And so subchannel in this context could be like one subchannel would be each IP address, and then the gRPC channel would be the logical channel for example.com, and then you would have some load balancing policy that says like do round robin over the various IP addresses returned by DNS. But it's also flexible enough where you could have your own system that returns that somehow maps logical names to IP addresses. That is not the same as DNS. Okay, so it's a logical grouping of channels. We've got reference, an identifier for this channel data, and some other stuff. I don't know what a channel ref looks like. I guess let's look at that. Channel connectivity state, unknown, idle, connecting, ready, transient failure, or shutdown. Channel data. Okay, we've got a target. The target this channel originally tried to connect to may be absent. It's a string. Channel connectivity state, channel trace, a trace of recent events on the channel may be absent. Number of calls started, number of calls that have been completed with OK status, and failed calls. Although I guess you can't record exactly what the status of the failed call was. And the last time a call was started on the channel. A channel event trace has a description of the event. A trace is an interesting thing that happened to a channel or a subchannel, such as creation, address resolution, subchannel creation, etc. Okay, so this is just like an event log. Unknown, yeah, it's just logging. Severity, info, warning, error, etc. Timestamp, and a child ref, which is, you can refer to a child object. What was that? That was a channel trace event. And then a channel trace has a number of events logged, the creation timestamp, and a list of events. I'm not sure why number of events logged would be different from list of events. Different from just calling the length of this field, but maybe. Oh, okay, here we go. This can this can differ from events.size because events can be overwritten or garbage collected by implementations. Okay. Channel ref is a reference to a channel. It's got a channel ID, which is in64. It's globally unique for this channel. Must be a positive number. An optional name associated with it, and intentionally don't use field numbers from other refs. Got it. Is that so we can pack them into one thing? A subchannel ref starts at 7. Okay. And it's basically the same thing. Socket ref is a reference to a socket. It's got a unique ID. It's got a name. And don't use other things. A server ref is the same thing. A server has a server ref and data. And then server data has things like a channel trace, a number of calls started, succeeded, and fails. And a socket has a socket ref data, whether it's local or remote. So gRPC, you can make requests to localhost, and that's kind of a way of doing interprocess communication. If you I assume it's slower than using some more direct method of interprocess communication, but it's pretty flexible. Socket data has number of streams started, whether which succeeded, failed, sent, received. The number of keep alive sent. This is typically implemented with HTTP2 ping messages. Some timestamp stuff. Socket options. Okay. Remote flow control window. There's some flow control stuff here. The amount of window granted to the local endpoint by the remote endpoint. This may be slightly out of date due to network latency. This does not include a stream level or TCP level flow control info. Cool. And then we've got some, an address has a TCP IP address, a UDS address, Unix domain socket address, an other address, I guess, which can be an any, so that you can implement your own addressing mechanism. And it's going to be one of these things, essentially a union over these types. And then security, we've got TLS, the cipher suite, the standard name, other name for the cipher suite. Whether a local certificate or remote certificate, and then other security, it's just any, and you can have TLS or other. And then socket options, the full name of the socket option. So it just has strings, name, value, and an any proto. So you can, I guess, pass in any socket option, and it will just, that'll just work. Socket option linker. I guess there's something called SO linger. I don't know. Socket option TCP info. And yeah, this bunch of TCP stuff. Channel Z is a service exposed by gRPC servers that provides detailed debug information. So channel Z has get top channels, get servers, get server sockets, get channel, get subchannel, get socket. Yeah, and that's all I'm going to look at for channel Z. Cool. And then math.proto, what is that doing? Hey, div args, we've got a dividend divisor, div reply, div args. Is this just for examples? Div many accepts an arbitrary number of division arguments from the client stream and sends back results from the reply stream. Div generates numbers in the Fibonacci sequence. Huh, what is this used for? Let's see if we can find fib args. So it's used in tests, in PHP tests and Ruby tests. I guess it's mainly for testing. All right, cool. So that's gRPC Proto. Did I close other stuff? All right, so let's look at source core. We have lib, ext, TSI, and plugin registry. README, the gRPC core library. This shared library provides all of gRPC's core functionality through a low-level API. gRPC libraries for the other languages supported in this repo are built on top of the shared core library. So things are built in C or C++. I think probably C++. And then the other implementations are just built using C bindings using some sort of foreign language interface, I believe. I don't know what ext is. Optional plugins for gRPC core. Modules in this directory extend gRPC core in useful ways. All optional code belongs here. Okay, so GCP transport, UPB generated. I'll wait for this emergency vehicle to pass. XDS, I think, is what they replaced the load balancing stuff with. But I don't know anything about XDS yet. So I think XDS is from Envoy. So maybe at some point we'll look at Envoy. Yeah, it's extensible something. It's not for TV metadata. It's not for the video game industry. XDS REST and gRPC protocol. I think common messages. Maybe this. There's the common expression language. That's, I think, different. I don't know. XDS configuration API overview. Envoy is architected such that different types of configuration management approaches are possible. The approach taken in a deployment will be dependent on the needs of the implementer. Simple deployments are possible with a fully static configuration. Many complicated deployments can incrementally add more complex dynamic configuration. The downside being that the implementer must provide one or more external gRPC or REST-based configuration provider APIs. These APIs are collectively known as XDS, Discovery Service. Okay. So some sort of discovery service API thing. So Envoy, I think, was started maybe by Uber or Lyft. Maybe Lyft. I guess let's look this up. But I believe that now some of Google's internal stuff is like re-implemented in Envoy. Envoy web server proxy. Originally built at Lyft to move their architecture away from monolith. Okay. Yep. All right. Cool. All right. So let's see. What is TSI? Transport something? Transport security interface, an abstraction over crypto and auth modules, typically OpenSSL. Okay. That's interesting, but that's not as interesting as getting to the heart of gRPC. So in source core lib, we have address utils, AVL, backoff, channel, compression, config, debug, event engine, experiments, GPR, gRPP, handshaker, HTTP, IAMGR, JSON load balancing, matchers, promise, resolver, resource quota, security, service config, slice, surface, transport, URI. Okay, so let's open AVL and backoff and channel. We'll ignore config and debug and compression. Event engine. I guess I don't know what these are, so I'm going to open them just so so that in case they're important. Handshaker, I guess HTTP is probably super core. IAMGR, I guess I'll open. Load balancing matchers. Promise, I don't think I need. Resolver and resource quota, I think I can do without. Security is super important, but I think that they may basically try to make everything go through TLS. So maybe there's not much interesting there. I guess I'll look at it. Service config, slice, surface, basically everything, transport and URI. And then I'll I guess aggressively close these so that we're not here forever. So AVL, we already looked at. This is an AVL tree. Let's remind ourselves what an AVL tree is. I think it's a self-balancing tree. Oops. I misspelled bang W for Wikipedia. Okay, so Adelson, Velsky, and Landis is a self-balancing binary search tree. It was the first such data structure to be invented. In an AVL tree, the height of the two child subtrees of any node differ by at most 1. Lookup, insertion, deletion all take O of log n, and in both the average and worst cases. Okay, where n is the number of nodes prior to the operation. Insertions and deletions may require the tree to be rebalanced by one or more tree rotations. And then we get an animation showing how to add stuff, and then you do a left rotation, and then you add more stuff, and it becomes unbalanced, and then you do a right rotation. Very cool. I'm not sure why. I don't have a good sense of why people choose one tree or another, but AVL trees seem good. I know that like in storage, different kinds of trees are used. I think in some of the compilers, we saw other sorts of fancy trees. All right, back off. So there's only the 2 files, really. So random early detection might be like an optimization, but we've got backoff and backoff.cc. Let's see. Initialize backoff machinery does not need to be destroyed. We've got a timestamp that gives you the next attempt time. You can reset the backoff. You can set the initial. You can set a multiplier. You can set the jitter. Initial backoff is how long to wait after the first failure before retrying. A multiplier is a factor with which to multiply backoff after a failed retry. Jitter is the amount of randomized backoffs, which is consistent with what I was saying before. Max backoff is the maximum time between retries. And that's really it. So we look at the implementation. I guess it's mostly exponential backoff, right? So next attempt, if we're in the initial attempt, then we're going to say initial is false because after this, we're no longer in the initial attempt. And we're going to return current backoff plus timestamp now. So, okay, so that gives you the timestamp of the next backoff. Rather than, so it's recording the timestamp rather than like a duration like 30 seconds in the future or whatever, which wouldn't, I guess, make a lot of sense. Because you wouldn't know when you read that variable what it meant, but a timestamp has the same meaning no matter when you read the variable. Current backoff is standard min of backoff times options multiplier or max backoff, sure. Duration is, so jitter from seconds as double. Abscil uniform, which I'm going to guess is the uniform statistical distribution. And I guess over an interval, maybe it's got 2 arguments. No, it's got 3 arguments. So negative options, jitter, positive options. Yeah, I think this is an interval, maybe an interval centered around 0 because we've got the negative here and the positive here. And then it's just jitter times current backoff seconds, and then you pass in a random generator. That's the first argument. Yeah, so that's like a uniform distribution. With who's within an interval around 0 defined by jitter times backoff seconds, I guess. And then you're going to return timestamp now, and then you can reset. And that's it. Although we're including, including algorithm. So let's see, next attempt time. Current backoff. I see. So I guess the way you get the maybe the way you get to be exponential is that you're continuously, not continuously, but repeatedly multiplying the back off times the multiplier. Is that what's going on? I think that's what's going on. Let's assume that's the case. Okay, so that's a really simple implementation. All right, here we are in gRPC core lib channel. We've got channel arguments, call tracer. Let's take a quick look at call tracer. Let's see, call attempt tracer, record received initial metadata, record end. Interface for a tracer that records activities on a call. Actual attempts for this call are traced with call attempt tracer after invoking record new attempt on the call tracer object. And so this is an interface for a tracer. Record send initial metadata, record received initial metadata, etc. Okay. We've got channel args. I guess let's look at channel args. Channel stack, sure. Channel stack builder, channel trace, channel Z, context. Let's look at a connected channel, a channel Z registry. I guess we'll ignore. Promise-based filter. Yeah, sure. Server call tracer, and just status util. Status util is probably not that interesting. Channel args. Okay. I don't know what iOS forward is. Okay. To do Hork. Hork is a good username. When we're ready to allow setting via a channel arg from the application, replace this with a macro and include blah, 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 blah. The gRPC internal event engine is something. Channel args are intentionally immutable to avoid the need for locking. Sounds good. There's channel type traits, which define a traits object for vtable lookup. Allows us to integrate with existing code easily, just define the trait, and allows some magic in channel args to automatically derive the vtable from a t star. To participate as a pointer, instances should expose the function static const gRPC arg pointer vtable. So some sort of vtable hack. I don't know enough about C++ vtables to know exactly what's going on, but maybe we can take a look. We've got pointer compare, doing some pointer comparisons. You got qsort compare. Okay, so pointer compare is going to call qsort compare for the two pointers and return some values. Okay, maybe that's something that the vtable needs to know. The vtable stuff, functions or whatever it's called. So the type returned by a calling ref on a t. Is this more vtable stuff? Ref type. Yeah, this is fancy. All right, specialization for ref counted pointers. Type should expose static and channel args compare. Channel arg type traits. Standard is base of ref counted channel args blah blah blah. Ref counted channel. Yeah. All right. And then we've got specialization for shared pointers. Incurs an allocation because shared pointer.release is not a thing. All right, you can check if we're a shared pointer. We've got channel arg type traits. And here's channel arg. Wait, are these all channel arg type traits? Struct. Yeah. So these are all just specializations, I guess, for different kinds of setups. Get object support for shared pointer and ref counted pointer. Provide the canonical name for a type's channel arg key. That's going to return there's the channel arg name. And then we've got, let's see, class channel args. And inside there's a class pointer. And it's got this qsort compare, which is going to return channel args detail pointer compare of this stuff. You're going to pass it in an A pointer, a B pointer, A's vtable, and B's vtable, I guess. I guess at some point I'll have to figure out what vtables are about. And maybe we can find, maybe there's some low-hanging fruit in vtables. Virtual method table. What does it look like? Consider the following class definitions in C++ syntax. Virtual, so class B1, we've got a virtual destructor, I guess. We got class B2, B2. And then class D, it's going to extend public B1, public B2. And we've got this code where we're going to call new B2 and new D. And GCC is going to produce the following 32-bit memory layout for object B2. Okay. Pointer to the virtual method table of B2 and value of int in B2. And the virtual method table of B2 is B2 : F2. And the following memory table layout for D. We've got the virtual method table for B1, for B2, the value of int in B1, int in B2, int in D. Note that those functions not carrying the keyword virtual in their declaration, which is F non-virtual and D, do not generally appear in the virtual method table. All right, I'm not sure. So if you happen to be watching this and know what's going on, then feel free to let me know. But I think the thing to take away from this when you see code like this that you don't really understand, and it's something low level-ish like gRPC, then my assumption at least is that the reason it's this complicated is that the Google code base is making gRPC calls all the time. And so these are just heavily optimized to take advantage of anything they can reasonably take advantage of to optimize the speed. That's my guess. Returns a union. Okay, so where we've got more channel arg stuff. gRPC must use result channel args. You can set the channel args with a name, I guess, for the arg and a pointer value. You can, how are these different? So a pointer value, an int value, a string view value, a standard string value, a const char star value, and just set it with gRPC arg, which I assume gRPC arg as a type mainly encapsulates a name and a value of some sort. So these are just, I guess, different ways to set a value, like convenience methods. A lot more templating stuff. Set if unset, remove, get string, get duration from milli, set object. So a lot of setters and getters. Some want minimal stack. Helpers for commonly accessed things. Okay. Let's see. And then let's see. Copy the argument. So we can do copy, normalize, union, find integer, get integer, returns the value of a arg subject to the constraints in A options. Similar to the above, but needs to find the arg from the name first. Okay. So you can get args in various ways. Yeah. Fun. Do we what is the CC file called? CC? Yep. I didn't see if it enumerated all of the possible args. But maybe they don't need to. Maybe those are those might have been what enumerated in the channel Z proto we looked at. I don't know. Okay. So that's args channel stack. I'm going to guess this is a stack of channels. Important note. When you update this API, please make the corresponding changes to the C++ API and source app comment channel filter HCC. I thought channel filter was a separate file, but we're going to start with a code comment about channel filters. A channel filter defines how operations on a channel are implemented. Channel filters are chained together to create full channels, and if those chains are linear, then channel filter stacks provide a mechanism to minimize allocation for that chain. Call stacks are created by channel stacks and represent the per call data for that stack. Implementation should take care of the following details for a batch. 1. Synchronization is achieved with a call combiner. If the filter wants to inject an error on the way down, it needs to call gRPC transport stream op batch finish with failure. A long name. From within the call combiner, this will cause any batch callbacks to be called with that error. If the filter wants to inject an error on the way up from a callback, it should also inject that error in the receive trailing metadata callback so that it can have the effect on the call. It can have an effect on the call status. So a channel filter defines operation on a channel. So we've got a chain of filters, which is a common sort of pattern with request processing. It's going to, I think that's what it's doing is you can request, so you can register various things on a chain, and that chain is going to pass it, it's going to manipulate the request somehow and then pass the request down to the next thingy in the chain. And there's some details about how you have to, some fiddly details about calling things so that stuff works properly. We've got a struct channel element args. It's going to be a channel stack with args, and it's going to keep track of the first and the last one. Call element args. Got a call stack or a pointer to a call stack. Server transport data. gRPC call context element. gRPC slice. GPR cycle counter start time. A deadline, I guess, for the call. An arena, which has, I think, something to do with memory. Let's look that up. And a call combiner. Is arena a general thing? Let's see if it's a general region-based memory. Okay, so it's just a region of memory. In computer science, region-based memory management is a type of memory management in which each allocated object is assigned to a region. A region, also called a zone, arena, area, or memory context, is a collection of allocated objects that can be efficiently reallocated or deallocated all at once. Like stack allocation, regions facilitate allocation and deallocation of memory with low overhead, but they are more flexible, allowing objects to live longer than the stack frame in which they were allocated. In typical implementations, all objects in a region are allocated in a single contiguous range of memory addresses, similar to how stack frames are typically allocated. Okay, so the idea here is that I think we saw this in call, right? So we're going to do region-based memory allocation for calls because there are so many of them. They can outlive the stack, what's it called? The stack frame. And they can be allocated or deallocated all at once. So that, I think, is the idea, is just to optimize allocation for calls because there are so many calls. And in gRPC, a call is like a request object. It contains all of the information that you need to make a call, including, I think, the request proto message, the gRPC context, and some other stuff. So let's see. Let's look at this again. So we've got a stack of calls, some data about server transport data, context element. So we've got the context, a path. I don't know what a slice is yet. We're going to have the record start time as a GPR cycle counter. I don't know what that means. Maybe it's a counter that's cyclic for some reason. We've got a deadline timestamp. An arena, I guess, in case we're using arena allocation. I don't know if we always use arena allocation. And a call combiner. And I'm not sure what a call combiner is, but perhaps it batches calls together, such as if you need to make similar calls repeatedly. Instead of sending 6 of them, you might send 1 or whatever and pretend there are 6. I don't know. Okay, so gRPC call stats is some sort of stat stuff, final info. So once the call is complete, we get stats and final status, which is defaulted to gRPC status okay, I guess, so that we don't have to keep setting it. And an error string, which is a null pointer. And here's gRPC filter stuff. Okay, so we can stream. Okay, called to, for example, send or receive data on a call. See gRPC call next op on how to call the next element in the stack. Members are laid out in approximate frequency of use order. Okay, so this is just the layout order in the struct is an optimization. Like I mentioned, everything is, we would expect everything to be heavily optimized. And that optimization might not show up in the history, the Git history of gRPC, because a lot of it will have been inherited from the lessons learned from Stubby, the internal RPC mechanism. Okay, we can create a promise to execute one call. If this is non-null, it may be used in preference to start transport stream op batch. Okay, so there's some make call promise. Okay. Called to handle channel level operations like new calls or transport closure. gRPC channel elem. gRPC transport op. Size of per call data. You can initialize per call data. elem is initialized at the start of the call, and elem call data is what needs initializing. The filter does not need to do any chaining. All right. You can destroy call elements. You get the size of channel data and some other stuff. All right. A channel element tracks its filter and the filter requested memory within a channel allocation. The channel element has a filter, a pointer to a filter, and some channel data. A call element tracks its filter, the filter requested memory within a channel allocation, and the filter requested memory within a call allocation. All right. And then a channel stack tracks a set of related filters for one channel and guarantees that they live within a single malloc allocation. So we've got a stream ref count, a call stack size, which is the memory required for a call stack computed at channel stack initialization. Remove this mechanism. It's a hack to allow channel to be separated from gRPC channel stacks allocation. Okay, so something on destroy, some manual constructor, event engine, and event engine. So here's some minimal infrastructure to act like a ref counted thing without converting everything. It's likely that we'll want to replace gRPC channel stack with something less regimented once the promise conversion completes, so avoiding doing a full C++ification for now. Okay, so that's some. I don't know what C++ification means. Does it mean that this is C and not C++? I don't really know how to check that. We get like standard. I mean, we've got like standard shared pointer. Does that exist in C or is that C++ only? I don't know. And then some call stack init stuff. Okay. I don't feel like I have a full understanding, or even maybe a rudimentary understanding of what the filters actually do. I guess let's take a quick look at the CC file and see if there's anything especially interesting there. We're going to round up to alignment size, do some alignment stuff, channel elements from stack. Panel stack init, per filter data, call stack init, some polling stuff, I guess. Okay, yeah, I don't know. Let's look at channel Z. All right, so we've got a channel Z node, a channel arg key for channel Z node. I don't know what makes it a node. Is it going in some sort of graph? A channel arg for indicating an internal channel, the default value for whether or not to enable channel Z. So I guess channel Z is optional. All right, so base node, base class for all channel Z entities. There are only 4 high-level channel Z entities. However, to support get top channels request, we split the channel entity into 2 different types. All children of base node must be one of these types. We've got a K top level channel, K internal channel, K sub channel, K server, and K socket. And we've got channel Z registry stuff, I guess, for registering channel Z. We've got a helper class. And here's a channel node. It extends base node. And what can it do? You can create one by passing it a target, a channel tracer max nodes, and whether it's an internal channel. You can get its name. You can get the connectivity state change string. You can render it to JSON. You can add trace events, record events, add child channel. And then a server node handles channel Z bookkeeping for servers. It's going to also extend base node. You can add child sockets, remove child sockets, add child listen socket, record call started, record call failed, and record call succeeded. So the server has access to the calls and can do bookkeeping about them. A socket node handles channel Z bookkeeping for sockets. And a listen socket node handles bookkeeping for listen sockets. All right, here's context. And let's see, what do we got? So call object context pointers. Call objects context pointers. So call context is represented as an array of a gRPC call context elements. Now, what is a? Is this like emphasize? Or does it mean that there's an anchor here, like a link? Call context is represented as an array of call context elements. This enum represents the indexes into the array, where each index contains a different type of value. So we've got context security, context tracing, value is a census context. Call tracer, where value is a call tracer object. Traffic is reserved for traffic class context. So I guess that's traffic control. Service config call data holds a pointer to service config call data associated with this call, and backend metric provider, which is, I guess, some sort of backend metrics. And gRPC core namespace. So bind the legacy context array into the new style structure. Okay, so we've got this enum, and it's going to include promise context.h. So maybe the real action is in promise context. And I did not open promise, I don't think. So let's take a look at the promise context.h. So here we are in promise context. To avoid accidentally creating context types, we require an explicit specialization of this template per context type. So what is a context? It's got some thread local stuff. Is that a big part of it? That it's got like thread local context? You can call with context. It's a template. And you pass it a type T and a type F. And what's it going to do? The standard move F into F underscore. Where did T go? Oh, T is the type of the context. And it's going to contextify, I guess, your F or whatever. Has context. Return promise detail context T get null pointer. So it's going to tell you whether it has context. You can get the context. And given a promise and context, return a promise that has that context set. That's with context. So given a promise and a context, you pass it in a T and an F. Promise detail with context, TF, standard move F, context. Yeah, okay. You can set a context on a promise, I suppose. But it doesn't seem like a context has much to it. So the constructor is, let's see, it's a template. You give it a type, and it's going to call, the whole class, I guess, is a template and it has a type, and it's got a P. Type T star P, and it's going to set current to P. So you're going to pass in you're going to give it a type and an object. It's going to set that object as the context, I guess. Not CC. Oops. Is there a C? Mycroft. What? I don't know. So we just have context.h. So it's just the header file. So then I wonder if there's anything interesting in GitHub search. Yeah, I'm not sure. All right, that's fine. Let's move along. All right, so here we are in core lib channel connected channel. And there's not much here. This is the header file. We have a bool function gRPC add connected filter, and you're going to pass it in a channel stack builder, star builder, and I guess it will return whether or not that succeeded. Connected channel. Does it have an implementation? Connected channel.cc. Let's see, connected channel data. We've got some transport data. Connected channel call data. Run and call combiner. So if you, run and call combiner is void. It takes a star arg. Is that the call combiner? And a gRPC error handle thing. The callback state will be set to static cast callback state of arg. So I guess the thing that you pass in is some sort of callback state. And then gRPC call combiner start. State call combiner. So we're going to take the callback state and call combiner on it. And we're going to also pass it the state original closure, the error, and the state reason. So it seems like it's, wonder if I'm curious what a call combiner is, but we'll I'll maybe do a search for this. Okay, so intercept callback. It's going to intercept the callback somehow. So we're going to pass it a call D, a callback state, a Boolean about whether to free when done, a reason, a closure, which is the original closure. And so where is state? Okay, so we're going to assign the state original closure to the original closure. The state call combiner, we're going to assign to call D call combiner, the call data call combiner. We're going to set the reason. And the original closure is going to be set to gRPC closure init of the state closure, which is different from the original closure. Free when done. And then we're going to, I guess, add, I'm guessing closure init is like a way of scripting kind of like things that happen in a closure. And so if we're going to free when done, then we're going to run cancel and call combiner. Otherwise, we're going to run in call combiner. And the thing we're going to run in call combiner is state gRPC schedule on exec context. state. Yeah, okay. I don't know. All right, callback state, get state for batch. Some batching stuff. And we perform a small hack to locate transport data alongside the connected channel data and call allocations to allow everything to be pulled in minimal cache line requests. So we've got transport stream from call data from transport stream. This says intercept a call operation and either push it directly up or translate it into transport stream operations. All right. Connected channel start transport op. Connected channel init call lm set poll set or poll set set. You've got a destructor for call data. And a bunch of other stuff. Let's see if we can find what this call combiner is doing. Oh, iomgr, I guess, is IO manager. Cool. So this should be a simple lock-free mechanism for serializing activity related to a single call. This is similar to a combiner, but is more lightweight. It requires the callback, or in the common case where the callback actually kicks off a chain of callbacks, the last callback in that chain to explicitly indicate by calling gRPC combiner stop when it is done with the action that was kicked off by the original callback. Okay, what is this? This is call combiner. Okay, and in call combiner, wait, where was that? A simple, so it says this is similar to a combiner, but is more lightweight. But we're in call combiner. So what is similar? I don't know. All right, so we've got class call combiner, and we're going to define a bunch of stuff. So call combiner start is going to call on call combiner the start function and pass in the closure, error, file, line, and reason. So call combiner closure, error, reason. And then we can call combiner stop. Yeah. Registers a closure to be invoked when cancel is called. Schedule closure, tsand lock, a fake ref counter lock that is kept alive after the destruction of gRPC call combiner when we are running the original closure. Ideally, we want to lock and unlock the call combiner as a pointer when the callback is called. However, original closure is free to trigger anything on the call combiner, including destruction of gRPC call. Thus, we need a ref counted structure that can outlive the call combiner. Sounds a bit dangerous. Is that dangerous? Sounds like they're faking out. It sounds like they're faking out tsand deliberately. All right, so call combiner closure list. Helper for running a list of closures in a call combiner. So this is going to help run closures in call combiners. And then we've got a call combiner closure. And what are we importing? We're in the header, right? Okay. Port platform inline vector, ATM, ref counted closure dynamic annotations, and MP SCQ. Does closure have any combiner stuff in it? No. So here's the CC file. Here's the tsand closure stuff. Call combiner start. So we're going to check if gRPC trace flag is enabled. And if so, we're going to log some stuff, I guess. We'll get the previous size of GPR ATM full fetch add. I don't know what ATM is. Check some more trace stuff if previous size is 0. Schedule closure. Else closure error. And then we're in the queue, we're going to push reinterpret cast multi-producer single consumer queue node star of closure. Call combiner stop is going to do some error handling stuff. Before the error handling stuff, it's going to reinterpret cast gRPC closure star queue pop and check end. I guess we're going to look at what's at the end. If the previous size is bigger than 1, that is. And that's going to give us the closure. And if the closure is null pointer, this can happen either due to a race condition within the MPSCQ code or because of a race with start. And we can, I guess, log some stuff. And we're going to get the closure error data. If closure error data, we're going to set it to 0. Then we're going to schedule the closure. Then we've got call combiner set notify on cancel. Call combiner cancel. Okay. So what is this MPSCQ stuff? What is it? MPSCQ. I think I saw it somewhere. Am I spelling it right? Okay. gRPP. What is gRPP? gRPR++, Google Portable Runtime for C++. Okay. The files in this directory contain various utility code for C++ code. None of this code is gRPC specific. Anything here may be also useful in other open source projects written in C++. This is one of the few places in source/core where we allow the use of portability macros. All right. So here is MPSCQ. Multiple producer, single consumer, lock-free queue. Okay. So it's a queue with a single consumer, and I guess the single consumer is going to be whatever thread is actually sending things out onto the network. But it's multiple producer. I'm guessing, and it's going to be potentially populated by any channels that are making a call or are manipulating the call. We can push a node, pop, and check end. It's just a queue. It's a queue with a fancy implementation that makes it lock free. Okay, and then let's just do a web search for gRPC call combiner. gRPC combiner explainer.md. Here we go. Talk by CTiller. Okay, so if there's a talk and an explainer, that means that I'm not alone in being, I guess, confused about what a call combiner is doing. The typical way of doing critical section is we're going to lock stuff with some sort of mutex, do stuff in mutex unlock. An alternative way is class combiner. We've got run f, which is going to mu lock f mu unlock, and it's going to mutex mu. And we're going to call combiner run do stuff. That's just putting the mutex stuff, I guess, in a function. I suppose if you have two threads calling combiner, then there will be some kind of queuing in place. It's called combiner because you can pass in more than one do stuff at once, and they will run under a common mutex. Okay, so you're getting mutex reuse. But run f. Okay, so I guess do stuff. Instead of just calling run, I guess you have a queue that gets populated and they all get run at once. The implementation described above has the issue that you're blocking a thread for a period of time, and this is considered harmful because it's an application thread that you're blocking. Instead, get a new property. Keep things running in serial execution. Don't ever sleep the thread, but maybe allow things to end up running on different threads from where they started. This means that do stuff doesn't necessarily run to completion when combiner run is invoked. So here we have class combiner. We have this multiple producer single consumer queue, which is going to be called queue. A multi-producer single consumer queue that can be made non-blocking. We've got some state S. Is it empty or executing? I guess. Yeah, right? So run F is if q.push F, I guess q push is going to return whether it succeeds or not. Q push returns true if it's the first thing. Okay, so if it's the first thing, then while q.pop and F, modulo some extra work to avoid races, we're going to call F. So this just shows us what happens if F is the first thing. Q push returns true if it's the first thing. Okay, so if F is the first thing, we're going to pop F and run it. The basic idea is that the first one to push onto the combiner executes the work and then keeps executing functions from the queue until the combiner is drained. All right, so things execute immediately, but I guess while it's executing, you can continue to add stuff. Is that the idea? Our combiner does some additional work with the motivation of write batching. We have a second tier of run called run finally. Anything queued onto run finally runs after we have drained the queue. That means that there's essentially a finally queue. This is not guaranteed to be final, but it's best effort. In the process of running the finally item, we might put something onto the main combiner queue, so we'll need to re-enter. CHTTP2 runs all ops in the run state except if it sees a write, it puts that into a finally. Okay, so writes go into finally, and finally are best effort. That way, anything else that gets put into the combiner can add to that write. All right. There's an extra way of delaying, like, I guess, buying time so you can add stuff to the right. Okay, so class combiner, we've got the Q, we've got the S, and another Q for finally. You can only do run finally when you are already running something from the combiner. So if Q push, we're going to loop while pop F, while F, while finally pop F. Okay, so while we can pop F, we're going to call F. I'm wondering if F is meant to be, like, F is the argument you passed in, right? But I thought you could pass in other stuff. Does it really mean the literal F, or is it saying, like, pop off the queue and run stuff until that's done, and then finally pop the end off and run it, and then go to loop again? Okay. That explains how, I'm not sure which one is right. I mean, maybe they do mean literal F, but I'm not sure. So that explains how combiners work in general. In gRPC, there is start batch, .tag, and then work only gets activated by somebody calling CQ next, which returns a tag. This gives an API level guarantee that there will be a thread doing polling to actually make work happen. However, some operations are not covered by a poller thread, such as cancellation that doesn't have a completion. Other callbacks that don't have a completion are the internal work that gets done before the batch gets completed. We need a condition called covered by poller. That means that the item will definitely need some thread at some point to call CQ next. This includes those callbacks that directly calls a completion, but also those that are indirectly required before getting a completion. The above combiner has the problem that it keeps draining for a potentially infinite amount of time, and that can lead to a huge tail latency for some operations. So we tweak it by returning to the application if we know that it is valid to do so. So while pop, call F if control can be returned, and some still queued thing is covered by poller, offload combiner work to some other thread. Offload is more than break. It does break, but also causes some other thread that is currently waiting on a poll to break out of its poll. This is done by setting the per polling island work queue distributor wake up FD. The work queue is the converse of the combiner. So offload really does work queue run, continue from while loop, and then break. This needs us to add another class variable for work queue, which is really conceptually distributed. Right. In principle, run finally could get starved, but this hasn't happened in practice. If we were concerned about this, we could put a limit on how many things come off the regular queue before finally queue gets processed. Okay. All right. So I wasn't really carefully following this, the kind of the tail end here where they were talking about more optimizations with polling and tags and next and whatnot. But principally, what's going on is it gives you a queue, a fancy queue that you can add stuff to, and kind of as a way of scheduling And that stuff that you've scheduled gets run under the same lock so that you don't have as much lock contention. And then we've got this finally optimization that you can put stuff off to the end if it's common for you to add stuff to a certain class of work, and that class of work is writes. Maybe I should read this again. In gRPC, there's a start batch tag, and the work only gets activated by somebody calling CQ next, which returns a tag. This gives an API level guarantee that there will be a thread doing polling to actually make work happen. Okay, so so you pass the batch a tag, and the work only gets activated by somebody calling CQ next. But what is CQ? Is CQ the I guess that's the non-blocking queue, maybe? At any rate, you need a condition called covered by polar. That means that the item will definitely need some thread at some point to call CQ next. This includes those callbacks that directly calls it completion, but also those that are okay. So there's a way of, like, I guess, naming a batch with a tag, and this ensures that the work is actually going to be done because there's a thread that's going to poll to make sure that it happens. Something like that. Okay, cool. So that makes a lot more sense. Here we are in source core lib channel promise based filter. .h, I think, right? .h. So we've got a channel filter, which has got some args. The arg is going to take a channel stack and a channel element. Perform post initialization step, if any. We've got some arena stuff. Make call promise. Start transport op. Start a legacy transport op. Return true if the op was handled. There's a legacy info call. There's a filter endpoint, which is either client or server. Designator for whether a filter is client side or server side. Please don't use this outside calls to make promise-based filter. It's intended to be deleted once the promise conversion is complete. So they're doing some sort of promise conversion. I guess they're adding promises where they previously had something else. Invalid character filter is a proxy channel filter for initialization failure, since we must leave a valid filter in place. Sorry, invalid channel filter, not invalid character. Okay. We've got base call data, which is for call data shared between all implementations of promise-based filters. And they've got an interceptor, a pipe sender, pipe receiver, and some, yeah, okay. Some polling stuff, activity implementation partial. You've got orphans and maybe non-owning waker and make owning waker. Right? Maybe that wakes up threads. I don't know. We can finalize. We can start batch. Scoped context, which has got context, call elements, polling, event engine, and call and context call context. We've got a flusher, which calls closures, schedules. The destructor calls closures, schedules batches, relinquishes call combiner. And yeah, we've got batches and pipes. Let's see, send message. A state machine for sending messages handles intercepting send message ops and forwarding them through pipes to the promise, then getting the result down the stack, split into its own class so we don't spend the memory initializing these members for filters that don't need to intercept sent messages. Okay, so send message takes base call data and an interceptor. You can start op. You can get pipe, wake, inside combiner, done. And then we've got state, which is starting state, no batch started, no outgoing pipe configured. We have an idle when we have an outgoing pipe, but no batches started. This is the steady state. Got batch, no pipe. When we have a batch started, but no outgoing pipe is configured. This will stall until we get a pipe. When we have then you can have a batch. You can be, we push the message to the pipe. Forwarded batch when we forwarded a message down the stack, and now we're waiting for a completion. And kbatch completed means we've got the completion callback. And canceled but not yet polled is we're almost done, but we need to poll first, and canceled. Okay. And then receive message, I guess, is going to be similar. Yeah. Cool. What else do we have? Server call tracer. I think this is going to record stuff. It's going to be kind of like some logging stuff. All right, status util. What is status util going to do us? Status code from string. Okay, this is like converting to strings and whatnot. Okay. Here's event engine. Common closures. Workable. Polar, POSIX. I guess let's look at slice and work queue. I'll look at these pretty quickly, I think. All right, common closures. Any invocable closure, self-deleting closure, and self-deleting closure, which I guess is the closure that deletes itself. Okay, forkable. It's experimental. Register fork handlers with the system, enabling fork support. This provides pthread-based support for fork events. Any objects that implement forkable can register themselves with this system using manage forkable. So does this mean that they use something other than fork by default, and that this is like support for fork? Potentially. All right, slice. I don't say event engine / slice. I think there's a slice outside of event engine, maybe. All right, but let's see what event engine slice is. We are going to import. Yeah, we're going to include. I'm looking at the CC file. We're going to include gRPC slice.h. So maybe I don't know. I don't need to look at this event engine stuff. All right, work queue. Experimental. A fast work queue based lightly on an internal Google implementation. It uses atomics to access the most recent element in the queue, making it fast for LIFO operations. Accessing the oldest or next element requires taking a mutex lock. All right, so it's a queue. All right, I'm sure the implementation is very interesting, but the API is going to be the queue API. All right, so GPR. This is the portable runtime stuff. We've got spin locks. I don't know what an ATM is. ATM, no barrier, clamped add. Oh, is it atomic? GPR, ATM value. Where's ATM.h? Do we not have one? I'm not sure. What is CPU.cc? A good number of cores, stuff like that. Okay. Here's gRPP. Wait, that's where we just were. Wait. Here's atomic utils. I think this is a different directory than we just were. There's GPR and there's gRPP. What is GPR? Oh, okay. So GPR is for C, ordinary C, and then gRPP is for C++. And what is crash? Void crash. Crash the program after printing message. All right, cool. Handshaker has a proxy mapper registry, and that's it. What is a proxy mapper? Proxy map, it determines the, okay, so we've got map name, determines the proxy name to resolve for a server URI. If no proxy is needed, returns null op. Okay, so I guess you can configure gRPC to use proxy somehow. All right, lib/http. We've got format request, HTTP client, security connector, parser. Let's just see what these, how involved these files are. Okay, the user agent for this library is gRPC HTTP CLI 0/0. Override functions return 1 if they handled the request, or 0 otherwise. So we've got some request stuff, post overrides, gRPC core, internally ref counted, tracks an in progress get or post request, calling start begins async work, and calling orphan arranges for async work to be completed as soon with 3 O's as possible, possibly aborting the request if it's in flight. So it's like abandoning the request potentially. Orphanable pointer get is going to asynchronously perform an HTTP get. You pass in URI, channel creds, and some stuff. And then post is also going to return an orphanable pointer. Then put. And that's, we got more. So we can finish, append error, do read, on read. So do read is going to, I guess, be guarded by this mutex. We're going to ref release and gRPC endpoint read, EP incoming on read, which is maybe a callback. Okay. You can indicate that you're done start writing. All right. And parser is this HTTP parsing. Maximum length of a header string of the form key value, 496. Okay. Yeah, this looks like, all right, so we've got headers. We've got HTTP first line, headers, body, trailers, end. Yeah, this is some parsing stuff. Okay, cool. Format request. Format get request, format post request. Is this just formatting it? Is it just taking the arguments and putting them into a proper buffer? Yeah, okay. It seems to just be writing the request in HTTP format, I suppose. All right, here's IO Manager. I think we looked at this briefly. Do we have a README? Platform abstractions for IO, mostly network. Provides abstractions over TCP, UDP, IO, file loading, polling, and concurrency management for various operating systems. Cool. I guess we're not going to look at this very carefully. TCP client, system D utils, socket, socket address, resolve address, port.h, poll set, lock free event, name ser, maybe name server, get host name stuff, fork POSIX, EV Apple. I don't know what EV is, maybe event, closures, combiners, block annotate, and event engine shims. Cool. Load balancing, we've got load balancing policy, load balancing factory. It was updated last month. Let's take a look at load balancing policy. Interface for load balancing policies. The following concepts are used, including channel, subchannel, resolver. Resolver is a plugin that takes a gRPC server URI and resolves it to a list of one or more addresses and a service config as described in this document naming. The resolver.h for the resolver API. And a load balancing policy. Load balancing policy has 2 parts, load balancing policy and a subchannel picker. The policy deals with the control plane work of managing subchannels. That's control plane stuff. And a subchannel picker, which handles the data plane work of determining which subchannel a given call should be sent on. Right? And here's the load balancing policy API. Interface for accessing per call state is call state. Implemented by the client channel and used by the subchannel picker. An interface for metadata. Do not make this a public API yet. Okay. We can, all right. So pick args, arguments used for picking a subchannel. The path of the call indicates the RPC service and method name, initial metadata, and call state. A backend metric accessor is an interface for accessing backend metric data implemented by the client channel and used by subchannel call trafficker interface. The subchannel call tracker interface, not trafficker, but the subchannel call tracker interface is an interface for tracking subchannel calls implemented by load balance policy and used in the channel. Pick result. Okay. There's some sort of queue. Pick cannot be completed Until something changes on the control plane, the client channel will queue the pick and try again the next time the picker is updated. Right, then we've got subchannel picker. The subchannel picker is the object used to pick the subchannel to use for a given call. This is implemented by the LB policy and used by the client channel to perform picks. Pickers are intended to encapsulate all of the state and logic needed on the data plane, that is, to actually process picks for individual calls sent on the channel. Cool. Then we've got channel control helper, which is a proxy object implemented by the client channel and used by the load balancing policy. Some config, args, a queue picker. Okay. Matchers. I'm not sure what matchers are for. Is this matching requests? And we're importing regular expressions, as you might expect for a matcher. String matcher, exact. The types are exact, prefix, suffix, safe, regex, or contains. Contains a string matcher instance, returns error, status is on failure. Header matcher, you can match headers. Yeah, I guess these are for like filters to match different calls. Okay. That's going to be my guess. All right, security, we've got authorization, certificate provider, context, credentials, security, connector, transport, and util. Is context security context? Let's just see what security context is. Okay, chained context is authenticated, peer identity property name. So who is the peer, ensure capacity, add property, add C-string property. So this context has credentials, which you would expect. The authorization or authentication, I'm not sure what auth means in this context, but auth context. And yeah, arena stuff. So mainly credentials and like things like what is the name of your peer, I guess. Service config. We don't really need to look at this, I don't think. The main purpose of the code here is to parse the service config in JSON form, which will look like this. Load balancing, method config. Okay, so it's just parsing configuration files. Slice. What is a slice? Right. Herein lies gRPC core slice and its team of thin wrappers around gRPC slice. They aim to keep you safe by providing strong guarantees around lifetime and mutability. The team is slice, provides a wrapper around an unknown type of slice, immutable since we don't know who else might be referencing it, and potentially reference counted. Static slice provides a wrapper around a static slice, not ref counted, fast to copy. Mutable slice provides a guarantee of unique ownership, meaning the underlying data can be mutated safely. This slice implementation is an extension of the event engine slice implementation defined. Hey, event engine slice was the thing I should have been looking at. Changes to this implementation might warrant changes to the public event engine slice type as well. Okay, so a C slice ref is going to take a gRPC slice. So what are we doing? We're including slice cast and slice from event engine, and we're including slice.h. I thought we were in slice.h. No, we're in lib/slice. Is this a file? So what about source? Is slice a... So where's gRPC/slice.h? We have gRPC event engine internal slice cast. Okay, so we're going to define gRPC core lib slice h. All right. What else do we got? Wait, did I do that? That's not what I meant to do. Yeah, I meant to grab this thing, right? Maybe I need a core. Source core? Hmm. What have I done? Let's go here in this other tab and then go here. Source core lib. So event engine here. And event engine slices here. Okay. And it's also importing gRPC / slice. So let's open this in a new tab. So we've got source. I think everything is relative to source. AppCL, C areas, compiler, core, CPP. Is it in CPP? Yeah, I don't know. How about we look up the gRPC docs? A wrapper around gRPC slice. gRPC slice, if initialized, represents the byte range s bytes, s.bytes 0 to s length -1. A gRPC, okay, it can have associated ref count, which has a destruction routine to run when the ref count reaches 0. See gRPC slice new. In gRPC slice ref, multiple gRPC slice values may share a ref count. If the slice does not have a ref count, it represents an inline small piece of data that is copied by value. As a special case, a slice can be given a ref count equals uint pointer t1, meaning the slice represents external data that is not ref counted. Okay, it's okay. Include /gRPC /impl /codegen /slice h. I see. All right. So it's some sort of block of, it's some sort of range of bytes, like an array of bytes, or a byte range. Is it just the range or is it the data? I think it's the data, right? And it can have a reference count associated to it, which has a destruction routine to be run. Okay. And so if the reference count goes to 0, then it gets destroyed. And multiple gRPC slice values can share a ref count. I'm not sure why you would want to do that. If it doesn't have a ref count, it's an inline small piece of data that's copied by value. Okay, so it's some sort of data sharing mechanism. I guess it's some way of sharing like an array of contiguous data, and that's reference counted and shareable, I guess, so that multiple multiple channels or whatever can, in the thread safe way, I assume, have visibility into the same slice. And then when it's no longer needed by the things that are using it, it gets garbage collected or whatever. I think that maybe that's what it's saying. So we've got a C slice ref, gRPC slice, and then if reinterpret cast uint pointer slice ref count is greater than 1, then we're going to slice ref count ref at loc, the debug location. Otherwise, we're going to return slice. If the ref count is bigger than 1, we're going to call this slice ref count ref. And I'm not sure what that's going to do. But if it's less than or equal to 1, I guess we'll just return slice. And either way, we're going to return slice because this is going to fall through. You can unref the slice, which we'll call unref, which I guess will decrement. I assume we'll maybe decrement the. I guess ref means increment the reference. So add another reference, and we're going to pass in the code location, maybe just for some sort of like tracking, so that we know who's referencing what. And unref, we're going to, I guess, pass in the same code location. And then we've got slice details. We've got a base slice, an iterator to access the underlying bytes. We can have begin and cbegin, cend, and it's going to return various pointers either to the start or the end. We can retrieve a borrowed reference to the underlying gRPC slice, retrieve the underlying slice and replace the one in this object with empty slice. You can take the slice, okay. More borrowed references, array access. We implement the operator square brackets, and that's just going to index into the slice. Yeah. Okay, so a slice is a some kind of like safe and optimized array is how I'm going to think of it. And I do feel motivated to see if I can find that includes the generated. Where is it generated? Yeah. Basil, CMake, etc. examples include? Did it include? Hey, gRPC. All right, here it is. Okay, so increment the ref count of f requires the slice to be initialized. Yeah, okay, slice new. It's going to take a pointer, a size, a length as a size, and I guess a destructor. Create a slice pointing at some data, calls malloc to allocate the ref count for the object, and arranges that destroy will be called with the pointer passed in at destruction. Okay, yep, cool. gRPC, so we're in Surface, the Surface directory. Services provide the bulk of gRPC core public API and translates it into calls against core components. Okay, so Surface, I guess, is Surface in the sense of like a attack surface. It's the thing you can get a grip on to call gRPC stuff. All right, and what can we do? We can channel init. We can call. I guess we should look at call log, call trace. Let's look at channel and channel init. Completion queue, event string, init internally, lame client. Yeah, let's look at lame client, server, validate metadata, and version. We'll just look at a few of these because I think we're getting a sense of how the system works overall. Okay, absale functional, any invocable function ref. So we've got some like function callable functions here. gRPC call create args. It's going to take a ref counted pointer to a channel. It's going to take a server. This is for creating a call, I suppose. A parent call, a propagation mask. I don't know what propagation mask, and I don't know why you need a parent call, but I'm sure there's a reason for that. Maybe for streams or something. So a completion queue. Okay, that's what CQ was in that other file. If not null, if we don't have a completion queue, so if we set a poll set alternative, it'll be used instead of a completion queue. I guess that's kind of like an optimization. A server transport data, slice that is the path, a slice that is the authority. And I guess these are path and authority are slices because they are reused repeatedly in different calls. We've got promise-based call, server promise-based call, server call context, call context, and we can update the deadline, increment the ref counter. gRPC call create will create a new call based on args. Regardless of success or failure, it always returns a valid new call into star call. Then we've got a gRPC call stack. We can start, batch, and execute, cancel. Okay. Surface channel. So this is just the I guess like publicly visible version of Surface. I mean, sorry, publicly visible version of channel. So the same as gRPC channel destroy, but doesn't create an exec context, and so it's safe to use from within core. Poll set call, registration table, etc. We've got ref counted channels, call size estimate, test only registered calls. I don't know what that means. Test only. Update call size estimate, channel, gRPC compression options. I guess this is it setting it or getting it? gRPC core channel from C channel, I guess it's a getter. Okay. Channel init. We've got a builder. Register stage registers one stage of mutators. Stages are run in priority order, lowest to highest, and then in registration order in the case of a tie. So we can register some stuff. We've got slots and create stack. Construct a channel stack of some sort. See stack.h, channel underscore stack.h for details. The lame client is do not take ownership of error. Okay. This filter becomes the entire channel stack for a channel that fails to be created. Every call returns failure. Okay, so this is essentially like a fancy version of not implemented. Something failed to initialize, and so it's going to tell you every time you call it that it's not working, I guess. Here's server.h. We're going to import a bunch of stuff. gRPC server config fetcher. I guess you have to fetch the server config. So server is going to extend ref counted server. But what is this other server? I don't think you can extend a ref counted version of yourself, can you? I guess it's, I don't know. Public CPP implementation of, I guess declaring that's the CPP implementation of server and gRPC underscore server. Okay, interesting. In this registered method, batch call allocation, an object to represent the most relevant characteristics of a newly allocated call object using allocating request matcher batch. So we've got an interface for listeners, listener interface, implementations must override orphan, channel args, some poll set stuff. Check whether you have open connections, config fetcher. I guess that's just setting the config fetcher. Starts listening for connections, you can call start. Sets up transport, creates a channel stack, and binds the transport to the server, called from the listener when a new connection is accepted. Register completion queue. There are functions to specify that a specific registered method or the unregistered collection should use a specific allocator for request matching. It's got a request matcher interface. I guess this is for dispatching to handlers. There's channel data, some allocation stuff, in the transport channel, CQ IDX, maybe that's index of the call queue, perhaps. Destroy some ref counting stuff, and then we have some call data stuff, whether it's pending, activated, zombied. Some shutdown logic. Here's the config fetcher struct. Class connection manager. Update channel args for connection. I don't know where it's fetching or why. We've got the watcher interface. It's invoked by the config fetcher when a new config is available. Implementations should update the connection manager and start serving if not already serving. Oh, I guess this is so that you can update your config. You can watch some thingy, like maybe a URL. And when a new config is available, they'll update the connection manager and start serving. Okay. I guess that's for pushing live config changes, maybe. Transport is a common implementation details for gRPC transports. Transports multiplex messages across some single connection. In Ext, there are implementations atop a custom HTTP2 implementation and atop Cronet. What is Cronet? Okay, it's a Chromium network stack. Okay. Yeah, so there's some TCP stuff, transport. I'm not going to really look at this. I am intrigued though by PID controller. Metadata, handshaker, error, connectivity, BDP. What is BDP? Let's look at BDP estimator first. Schedule a ping, start a ping. BDP, bandwidth delay product. Is that it? The product of a data link's capacity and its round trip delay time. Okay. You're going to multiply the capacity by its delay time. The result, an amount of data measured in bits or bytes, is equivalent to the maximum amount of data on the network circuit at any given time. That is data that has been transmitted but not yet acknowledged. So here's PID controller. The simple PID controller, it implements a proportional integral derivative controller used when we want to iteratively control a variable to converge to some other observed value. No. Okay, let's try this again. Simple PID controller implements a proportional integral derivative controller used when we want to iteratively control a variable to converge some other observed value to a set point. Gains can be set to adjust sensitivity to current error, the integral of error, and the derivative of error. Yeah, it's a PID controller. But why? Where is this used? Maybe for, I guess it's in networks, so it must be used for like bandwidthy stuff. Okay, so here's where it's defined. Where is it used? Okay, flow control. Okay. So they're using a PID controller for flow control, which seems smart. I thought there were standard algorithms for that had to be used, but maybe not. Here's the implementation. It's fairly not a whole lot going on. Very cool. URI, lib/URI just has URI parsing, which we will ignore. And then we're done. All right. That was extra long. I think that was longer than my usual videos. But there was a lot going on there. And that was fun. That's all for me. I'll be back tomorrow for Tools Tuesday. All right. See you then. Thanks.